Europe could become a frozen wasteland by 2057 if the AMOC, or Atlantic Meridional Overturning circulation, collapses. But scientists just discovered something incredible. Thousands of invisible ocean vortices might save us. Here's how whirlpools the size of cities are rewriting our climate's fate, and why we only just noticed them. The scientific community studying our planet's climate is deeply worried. The AMOC, that system of Atlantic currents that keeps Europe's climate mild, is showing signs of slowing down. Several recent studies suggest it could weaken drastically by mid-century, with significant consequences for Northern Europe's climate. Models are talking about possible temperature drops of several degrees, much harsher winters, and impacts on agriculture. This isn't science fiction. We're talking about changes that could affect hundreds of millions of people within just a few generations. Populations that would have to completely rethink their way of life, or resign themselves to migrating to less compromised latitudes. But here's the plot twist. What if our climate models have been nearsighted? What if we've been missing something fundamental simply because our computers aren't powerful enough to detect it? Well, welcome to the world of ocean eddies, the invisible vortices that could rewrite everything we thought we knew about Europe's climate future. But let's take a step back. The AMOC, Atlantic Meridional Overturning circulation, for those in the know, is basically Europe's central heating system. Here's how it works. Warm water rises from the tropics, travels north, cools near Greenland, sinks, and heads back down. Simple, right? But the numbers are mind-boggling. This invisible river transports 15 million cubic meters of water per second. To put that in perspective, try to imagine a cube 820 feet or 250 meters on each side, full of water that fills and empties every second. And it's precisely thanks to this mechanism that Northern Europe enjoys a decidedly better climate compared to locations at that same latitude. London and Calgary in Canada are both around 51 degrees north, for example. Yet, while Calgary in winter can hit minus 22 degrees Fahrenheit or minus 30 degrees Celsius, London barely drops below 23 degrees Fahrenheit or minus 5 degrees Celsius. This difference, which averages about 18 degrees Fahrenheit or 10 degrees Celsius between the two cities, is largely due to the AMOC. Without this system of currents bringing warm water from the tropics, London would have temperatures much more similar to Canada's. It's the AMOC that makes Western Europe abnormally mild for its latitude. Without it, Europe would be a frozen extension of Canada. The problem is that with global warming and Greenland melting, we're pouring fresh water into the Atlantic like it's a giant bathtub. From 2000 to 2020, Greenland lost an average of 280 billion tons of ice per year. And once again, try to imagine an ice cube 3.7 miles or 6 kilometers on each side melting into the ocean every year, sweetening the ocean water. What happens? Fresh water is lighter, it doesn't sink, and our precious conveyor belt risks jamming. This is where the story gets really interesting. Based on this data, in recent years, climatologists have split into two opposing camps. On one side, the doomsayers, led by Danish and Dutch scientists who, using sophisticated statistical analyses and real ocean data, predict the AMOC will collapse between 2025 and 2095, with the most likely date being 2057. We're 95% certain, they say. Get out your fur coats. On the other side, the optimists, mainly traditional climate modelers who maintain the AMOC will hold out at least until 2100. Our CM-IP6 models are the most advanced in the world, they counter. We don't see any imminent collapse. Meanwhile, 44 of the world's most important climatologists signed an open letter in October of 2024, declaring that the risk has been enormously underestimated and that the AMOC could collapse in the coming decades with devastating consequences. The tension in the scientific community was palpable, with conferences that looked like boxing rings, papers contradicting each other, vitriolic tweets between usually composed professors. And then suddenly, the eddies entered the scene, our invisible heroes. But what the hell are they? Eddies are ocean vortices, like little water tornadoes spinning in the ocean. They range from 6 to 60 miles or 10 to 100 kilometers in diameter. There are thousands of them in the Atlantic, being born, living for weeks or months, then dying, like bubbles in a pot of boiling water. Think of them as the spoons stirring coffee in the ocean. Without them, warm and cold water, salty and fresh, would remain separated like oil and vinegar in a bottle. But eddies mix everything up, creating a much more dynamic system, transporting and distributing heat, salt, and nutrients. Some rotate clockwise, others counterclockwise. They attract, repel, merge, divide. It's a chaotic ballet, but with precise rules, governed by the laws of fluid physics. Eddies are three-dimensional structures that reach down to the depth where water density changes rapidly, typically between 1,640 and 3,280 feet, or 500 and 1,000 meters deep. In the Arctic, three types have been identified: surface eddies, mid-depth double-core eddies, and deep eddies, capable of reaching 6,560 to 9,840 feet, or 2,000 to 3,000 meters. Their average rotation speed is about 0.4 miles per hour, or 700 meters per hour. It might seem slow, but on scales of tens of miles, it's a significant rotation. Contrary to what you might think, many eddies are visible even at the surface. Satellites can detect variations of even just 0.8 inches or 2 centimeters in sea level, and eddies create ripples on the water of exactly these measurements. They can also be recognized by surface temperature differences, and in areas with partial sea ice, they create streaks and patterns visible in the ice that acts as a passive tracer. The name? It comes from English and simply means vortex or whirlpool, just like the ones you see when you empty the bathtub. And it's not like we discovered them yesterday. Oceanographers have known about them since the 1970s, when the first satellites began photographing the ocean and saw, though not exactly in visible light, these giant spirals spinning in the water. The problem wasn't knowing they existed, but understanding what they really did. It was like knowing bees exist without understanding they're the ones pollinating flowers. For decades, we knew they were there. We measured them, photographed them, studied them individually, but we couldn't put them in global climate models. Why? Simple. We didn't have powerful enough computers. Including thousands of vortices in a simulation of the entire Atlantic was like trying to model all of Europe's traffic by tracking every single car. Technically impossible until very recently. Only in recent months, with the arrival of supercomputers capable of billions of calculations per second, have we finally been able to see what happens when we include eddies in the AMOC simulations. And this happened at Utrecht University, where for the first time they ran a model that included thousands of eddies. They simulated 600 years of ocean evolution, pumping virtual fresh water into the Atlantic to see when the AMOC would stop. And it was like putting on glasses after years of myopia, says Renee Van Westen, one of the lead researchers. Suddenly we were seeing structures and mechanisms that were completely invisible before. The result was shocking. Hey Curious Squad, before moving on, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. Yes, the AMOC was slowing down, but it wasn't collapsing like in low-resolution models. The eddies were jumping into action like an emergency response team, redistributing energy and maintaining circulation. But the most surprising discovery was something else. The new models show that eddies act as a kind of ocean immune system. When the AMOC begins to weaken in one area, eddies redistribute the energy, maintaining the general flow. It's like having thousands of little backup pumps that kick in when the main system limps along. We always thought of the AMOC as a highway, explains a German researcher, but in reality it's more like a road network with thousands of alternative routes. If the main highway gets blocked, traffic can detour onto secondary roads. Now comes the really intriguing and somewhat disturbing part. Eddies could save the AMOC globally, but they also create new local tipping points. It's like discovering that your security system has fuses. They protect the general system, but they can blow individually. In short, high-resolution models have revealed something no one expected. Instead of a single big on-off switch for the entire Atlantic, there are dozens of smaller switches. Some regions could experience local collapse, while the rest of the ocean continues to circulate normally. For example, circulation in the Labrador Sea could shut down, while that in the Norwegian Sea could continue, or vice versa. It's both good and bad news, admits a Norwegian oceanographer. Good because the total system is more resilient, bad because we could have very unpleasant regional surprises. Imagine Bergen, Norway. The models show that even with eddies maintaining the overall AMOC, the city could see winter temperatures plummet by 63 degrees Fahrenheit or 35 degrees Celsius in a century. From winters at 23 degrees Fahrenheit or minus 5 degrees Celsius to winters at minus 40 degrees Fahrenheit or minus 40 degrees Celsius. It's not the global apocalypse, but tell that to the people of Bergen. But wait, there's one last plot twist that even Hollywood screenwriters wouldn't have dared. And it comes from the most unexpected place, Antarctica. In February 2025, a study published in Nature dropped a bombshell. Models show the AMOC can't completely collapse unless a compensatory circulation forms in the Pacific Ocean called PMOC. It's pure physics. If water rises in the Southern Ocean, and it does, pushed by winds, it has to descend somewhere. Normally, it descends in the Atlantic via the AMOC. If the AMOC stops, it should start descending in the Pacific. But here's the kicker. The Southern Ocean winds are so strong and constant that they force at least a minimum of Atlantic circulation anyway. It's as if nature installed an idiot-proof safety system. It was a revelation, admits Laura Jackson of the UK National Oceanography Centre. For years, we focused only on the North Atlantic, and meanwhile, the key was on the other side of the planet. The Antarctic winds, blowing incessantly from west to east, are the system's true backup engine. And there's another surprise. While everyone expected the Southern Ocean to become less salty with melting ice, the opposite is happening. It's getting saltier. Nobody knows exactly why, but it could be another natural protection mechanism we hadn't considered. Obviously, not everyone has embraced this new optimistic vision. Critics raise very valid points. Even high-resolution models have to make approximations, emphasizes Peter Ditlevsen of the University of Copenhagen. Eddies smaller than 6 miles or 10 kilometers are still invisible to our satellites and could be the ones making the final difference. The Greenland factor remains a ticking time bomb. Many models still underestimate how much ice is melting. Jason Bach's Greenland ice sheet expert warns that if we include extreme melting events like that of 2012, when we lost 450 billion tons in a year, all models go to hell. And then there's the speed of change. Models assume gradual change. Well, what happens if Greenland has a terrible year and dumps enormous amounts of fresh water all at once? It's like testing a dam's resistance with a steady flow of water, explains Stefan Ramstorff of Potsdam. And then a tsunami arrives, and the eddies themselves could be vulnerable. Some studies suggest that with a more stratified ocean, fresh water on top and salty below, eddies could weaken. We're assuming our saviors will remain strong, says a critic, but they could be the first victims. A Danish climatologist puts it this way. It's like saying your car has airbags, so you can drive at 125 miles per hour or 200 kilometers per hour. Eddies help, sure, but they're not a magic wand. So should we worry or not? The answer, frustrating but honest, is that it depends. The immediate ice apocalypse, a la the day after tomorrow, seems much less likely. We probably have 20 to 30 more years than expected to act on climate change. The system is more resilient than we feared with backup mechanisms we didn't know about, and the technology to monitor eddies is rapidly improving. But the AMOC is still weakening by 0.46 sphere-drops per decade since 1950. A sphere-drop is a unit of measurement in oceanography equivalent to a flow of 1 million cubic meters per second. Some regions could experience dramatic changes even if the global system holds up. We still don't know everything about eddies, and there could be surprises, and the cost to adapt even to limited changes will be astronomical. And then there's the weird but true news. London's fate could depend on vortices in the ocean south of Argentina. We might have to thank Antarctic winds for French vineyards, and future European winters could be patchy, with Oslo at minus 40 degrees Fahrenheit or minus 40 degrees Celsius, while Hamburg's climate remains mild. The real challenge now is monitoring these eddies in real time, even though it's like trying to count bees in a swarm while they're flying. They move, change, appear, and disappear. The technology we're developing is science fiction. Satellites that can't see variations of millimeters in sea level. 3,000 Argo robots that dive and resurface in the ocean, measuring temperature and salinity. Submarine cables that sense the magnetic field generated by moving salt water. Autonomous underwater gliders that can follow a single eddy for months. We're building the ocean's nervous system, explains Eleanor Frachka Williams, who leads part of the RAPID project. Sensors everywhere connected in real time to understand what these vortices do. It's like going from a blurry photo to a 4K movie. The cost? About $2.2 billion or 2 billion euros for the next 10 years. Seems like a lot? European agriculture is worth 220 billion or 200 billion euros a year. Tourism, 550 billion or 500 billion euros. If the AMOC collapses, we can kiss both goodbye. Maybe 2.2 billion to understand what's happening isn't that much after all. There's an almost poetic irony in this whole story. For decades, we feared global warming would roast us. Then we discovered it could freeze us, at least in Europe. Now we discover that invisible little vortices could save us. But the real irony is something else. The more sophisticated we make our models, the more complex the ocean reveals itself to be. Every answer generates 10 new questions. It's like peeling an infinite onion. Every layer reveals new surprises, and sometimes makes you cry. A veteran oceanographer sums it up like this. In the 80s, we thought we understood the ocean. In the 90s, we realized we didn't understand anything. In the 2000s, we thought we finally understood that we didn't understand. Now in 2025, we've understood that we didn't understand that we didn't understand. In short, eddies teach us a lesson in cosmic humility. For decades, we've studied the ocean as if it were a giant pool with orderly, predictable, modelable currents. Instead, it's more like a pot of boiling water. Chaotic, turbulent, full of vortices interacting in ways we're only beginning to understand. This doesn't mean we can relax. The AMOC is still in danger, the climate is still changing, and Europe could still face much colder winters. But maybe, just maybe, we have invisible allies working for us in the ocean depths. The next time you see a whirlpool in the sink water, think of ocean eddies, little vortices that could make the difference between a livable Europe and a frozen continent. Not bad for something we couldn't even see until yesterday, right? But above all, let's remember that nature is always more complex than we think, and that sometimes our salvation could come from the most unexpected places, like invisible vortices 10,000 feet or 3,000 meters under the ocean surface, created by winds blowing from the other side of the world. It's not reassuring, but it's damn fascinating.